Common mode noise, such as ground loops, can be much more difficult to deal with. One real-world, effective solution is the isolation transformer, and the most effective of these are the true symmetrical balanced isolation transformer. Here's how one works. True symmetrically balanced power is achieved by running the incoming AC line into 1-to-1 ratio isolation transformer with a precisely placed center tap on the transformer's output or secondary. The incoming voltage, 120 volts AC on the line terminal and 0 volts AC on the neutral and ground, are split in perfect halves on the secondary of the transformer. The output line terminal now has 60 volts AC and the neutral terminal has 60 volts AC when referenced to its new center tap ground, which remains at 0 volts AC. What's significant about this is that the two 60 volt AC terminals are now in opposite polarity, so the symmetrical AC noise or common mode fields cancel. This noise reduction is extraordinarily efficient and linear across a huge frequency range or bandwidth. The transformer has completely reworked your incoming AC, and the result is perfectly clean power devoid of common mode noise. Think of it this way. It's like balanced audio, but at a higher voltage. Though there are many types of isolation transformers, they are not equal. An isolation transformer that is not symmetrically balanced will reduce a great deal of common mode noise as long as it's been created with proper ground strapping and an effective Faraday shield to minimize capacitive coupling. However, without precise balancing, the noise reduction is typically not as great nor as linear, which is critical for maximizing system performance. There are many form factors or shapes for isolation transformers. The traditional EI type is the squarest package most people associate with a transformer. This type of transformer has two significant problems. The first is its tendency to propagate a huge magnetic field when any significant AC load is present. This can easily couple hum into adjacent equipment for a distance of up to 5 feet in many cases. The second is the relative inefficiency or poor regulation of this type of transformer. As the current demand rises, your output voltage will drop significantly. Toroid or donut-shaped transformers have a big advantage here, as the field of radiation is considerably reduced, allowing rack mounting near sensitive equipment, for example. And regulation can be maintained at nearly 98%. This means that as current demand rises in your system, the voltage coming out of your transformer will be very close to that going in. This is simply not possible with conventional EI transformers. Another important attribute with true symmetrical power is total isolation from ground. This has the advantage of breaking the noise that is present on the AC mains, but the greatest advantage is breaking ground loops. Even in a situation where the location is star grounded, one or more remote components can create a ground loop. With an isolation transformer that has an isolated or floating output, we may effectively isolate one or more offending components, thus breaking the noise loop. To do this, it is critical that the transformer be safeguarded with a GFCI ground fault circuit interrupt. This protection device assures that if there is any current leakage from line to ground or neutral to ground in excess of 5 milliamps, the circuit disconnects. This assures safe operation well beyond even that of a typical AC tap.